Alright, in the Coriolis effect notes for 414, I said these are some videos. We actually saw all of these videos today during the Tuesday Zoom meeting. What I wanted to do is go over them again for everybody who wasn't at the meeting. So here's the first one. It's from National Geographic Channel.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion.
All right, here's the game, right? You're going to throw the ball straight to, what's your name, Victor, right? But this time, I'm going to complicate things slightly. I'm going to rotate to the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
Yeah.
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah. I don't know.
Right, what's going to happen, dude?
That's going to veer off to the left.
So the ball is going to swerve off to the left.
Yep.
And you might catch it.
Possibly.
Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me, and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, is that everyone? No, hang on, one more. Spencer.
He's not arrogant.
Just quietly
He's
confident.
not catching it. He's
Really?
not catching it, no.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying to come to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right?
Make your hypothesis.
Right, in your own time, throw the ball.
I got this.
So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw?
Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
Yeah, it did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we all agreeing here the ball curved in midair.
Yeah.
Yeah.
And you didn't cheat this at all.
No, I didn't.
Okay. And do you know why it did that?
No.
No idea. It's called the Coriolis effect. And
Coriolis.
it's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight, still going straight, but the table is moving below you, and all of a sudden, look who's in front of that straight moving ball, and it looks like it's bent off to the right because you're still looking at the guy you're intending to throw it to, and that, ladies and gentlemen, is a Coriolis effect.
Yay. So, he's right. You cannot throw a projectile in a curve. You can't make a bullet go to the side, you can't make a baseball go to the side, you can only throw in a straight line. But what happens is the target is moving. As you saw, the person rotated out of the way. And that's what happened here. As the person rotates out of the way, if you were the ball, you say, yeah, I'm going straight, and the person's rotating away. But since you're on the merry-go-round, you see the ball move. Because you're stationary compared to everything else. Your frame of reference is already spinning. So what you see then is the movement of the ball. The same way that if you're riding in a car, you don't see yourself moving in the car. But if you look out the window, you can see the trees moving. We all know that it's not the trees actually moving, it's you moving. But in this case, it depends on where you're at. Are you the tree or are you in the car? So here's another demonstration. This one's from MIT. So here we see the same setup, this time with actual scientists and not just athletes. They throw a ball in a straight line, because you can only throw a ball in a straight line. But they're on a rotating platform, so what happens when they start rotating? How'd that happen? So you can tell by looking above, you're not rotating. You can see the ball move in a straight line. When he throws the ball, it only moves in a straight line. It was the other person that moved to the side. He throws the ball, and the other person is the one moving out of the way. He throws the ball, goes in a straight line. It's the other person moving out of the way. But if you're the one who's spinning, you don't see it that way. You see yourself as being straight, and it looks like the ball is bending. It looks like that flight path is curved. And that's the Coriolis effect. That's what happens to the wind in the atmosphere. These global winds, as they travel from the poles towards the equator, they travel across the spinning Earth like this. And so on the way there, they actually get deflected. In the northern hemisphere, it always bends to the right because we turn counterclockwise. And that's the direction this guy is bending here too. He's going counterclockwise. And you can see the ball going off to his right. Because he's going counterclockwise, just like the Earth does in the northern hemisphere. It's bending to his right, the way we think the wind does. But now he's spinning the opposite direction, and this is what happens in the southern hemisphere. Because instead of looking from the top down, you're looking at the bottom up. It looks like the Earth is going clockwise, like this guy is going clockwise. And so it actually bends to the left, or instead of the right. That is his left. Alright, and here's our next video. Sorry about that.
Picture a circle. Here's its center, here's point A, and here's point B. Point A is twice the distance from the center of the circle than point B. Oh yeah, and it spins from its center. In 2 seconds, both points do one full revolution. But to go all the way around, point A has to go this far, while point B only has to go this far. And we all know if something travels a greater distance in a shorter amount of time, it must be going faster. So point A...
So what he's saying is the further out from the center, from the axis you are, the faster you go. And that's true. The fattest part of the Earth furthest away from the axis, is the equator. And so the equator spins faster.
A must be moving faster than point B. Okay, now swap out this flat circle for the Earth, and the same thing is true. All points closer to the center, say like someone in Greenland, will be spinning slower when compared to points spinning further away from it, say like people in Brazil, closer to the equator. So, if we look at it all flattened out, we can picture something like this. Arrows at the equator travel faster than arrows at the 45-degree line, like we just observed. Now, imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north, where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else.
So what he's saying is you started out moving faster. As you move north, you're still moving faster than the land is and then the air is up here. So it looks like you're speeding up. In reality, you were going fast all along. We just didn't see that curvature. But since we're the ones who are moving fast, we see it like the cloud is curving.
If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you. But if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind.
And so this is what we saw in the last video as well. It wants to go straight, but by the time it gets here, the Earth has already spun in this direction. So this is the location now that's right there.
And the same things for the southern hemisphere. Moving toward...
And it happens the opposite way in the southern hemisphere. When I go towards the equator, I slow down. When I go away from the equator, I speed up. I'm going to skip this next part because the arrows bend the wrong direction and I don't want you to get confused.
Imagine a low-pressure cell. That means all the air around it will get sucked into the center. But the air coming from the equator will be traveling faster, so it will deflect to the right, while the air coming from the poles will be moving slower, so they'll fall behind and deflect to the left. What this results in is a circular air current spinning counterclockwise. And that's exactly what hurricanes are, low-pressure cells spinning because of the Coriolis effect. Moving this example down to the southern hemisphere, things are reversed. A low-pressure cell will still suck in the surrounding air, but now the air coming from above will be moving faster, again deflecting to the right, while the air coming from below is moving slower, again falling behind by moving to the left. This results in a clockwise spin, which is why storms in the southern hemisphere spin this way. And that's about it. It's a short video, and that's kind of the...
Yeah, so the Coriolis effect spins in different directions in different hemispheres. Things tend to spin counterclockwise in the northern hemisphere where we live, and it spins clockwise in the southern hemisphere. That's because in the southern hemisphere, everything is bending to the left, and in the northern hemisphere, everything is bending to the right. So here's the last video.
Hey, Australian people, have you ever been...
Okay, so let me preface this. Most people know the Coriolis effect because they say that's why water swirls down the drain in a specific direction. He's here to dispel that notion. Coriolis effect only happens on a global scale. It does not work on draining water like in a toilet.
Hey, Australian people, have you ever been in the Northern Hemisphere? Have you ever noticed whether your toilet drains differently than it does here? No? You heard maybe it has something to do with the Coriolis effect? Welcome to another edition of I Don't Think It Means What You Think It Means. You probably don't spend a lot of time thinking about how water drains from your toilet, but somehow the idea that water drains differently in the northern and southern hemispheres has made its way into our collective consciousness. Furthermore, the reason for this phenomenon has been pinned to the Coriolis effect, which refers to the way the Earth's constant eastward rotation influences how we view the trajectory of certain moving objects. Because the diameter of the Earth at the equator, at 40,076 kilometers, is so much greater than it is at the poles, at 0 kilometers, the land of the equator is moving lots faster than the land everywhere else, about 1,638 kilometers per hour.
That is about 1,000 miles per hour at the equator.
At the equator compared to about half that at 60 degrees north latitude and pretty much stationary at the poles. And yes, the Coriolis effect, named for 19th century mathematician Gustav Coriolis, does indeed influence objects traveling across the face of the Earth due to this constant eastward rotation. If you tried to throw a baseball from the equator up to your friend standing at the North Pole, your ball would appear to veer to the right because it would maintain the greater momentum of the place it started from. On the other hand, if you were throwing the ball to the South Pole from the equator, the ball would appear to veer to the left for the same reason. So although the Coriolis effect is totally a thing, the application of this principle to draining water in Earth's two hemispheres is just bunk. Our planet spinning around once every 24 hours isn't a big enough deal to affect a toilet that takes 5 seconds to flush. Basically, the direction water drains is dictated by the shape of the basin it's in, the sink or toilet bowl or whatever. The Coriolis effect does, however, influence bigger, slower-moving fluids, global air and ocean currents.
Yeah, and if you remember the ocean currents maps, they do form those gyres, those huge circles in the ocean. The same is true with these air currents that we're studying now,
for instance, which can end up giving hurricanes their spin. If the Earth didn't rotate on its axis, among the very many and unpleasant things that would be different, one of them would be that winds wouldn't blow either west or east. They'd flow from the poles, which are naturally high-pressure areas, to the equator, where there's low pressure, and back again. But the Coriolis effect deflects these winds to the right in the northern hemisphere, to the left in the southern hemisphere, which creates weather systems that rotate clockwise in the northern hemisphere and counterclockwise in the south.
So what he's saying is that without the Coriolis effect, we would see the straight vertical movement of air. It would go from the pole to the equator, or from the pole to the equator. But instead, since the Earth is moving, it's always curving. The air curves along this path.
In the south. Coriolis effect working at that scale does affect entire climate patterns, but it can't make itself felt on whatever you left in your toilet. Sorry. The Coriolis effect. Weather, not toilets. Got it? Good. Thank you for watching.
Alright. So there's one more video. I'm going to put this in a different Ed puzzle because I think it's so important. I hope y'all enjoyed seeing these, and hopefully my commentary wasn't too terrible. Thank you.